Question 8 involves probability and statistics. We're told that an online word game involves trying to guess a 5-letter word in as few attempts as possible. In the game, each player is given a score based on how many attempts it takes them to guess the word. Part A says that in Ireland, players' scores are approximately normally distributed, with a mean of 3.87 and a standard deviation of 0.36. A player is selected at random from the players in Ireland, and we must find the probability that this player has a score which is less than 3.5. The first thing to notice here is that we're working with a normal distribution. Our formula book contains probability tables full of information on this distribution, and this will be the key to solving this question. However, before we can use these tables, we must standardize our data. We do this by calculating the z-score. The formula is that z is equal to x minus mu all over sigma. Here, x refers to the target value, and in our question the target is 3.5. Mu is the mean, and in our question that's 3.87. Sigma is the standard deviation, and here that's 0.36. Subbing in these values and computing the answer gives us minus 1.027778. The tables in our formula book are formatted to receive numbers which have exactly 2 numbers after the decimal place, so we should round this number to 2 decimal places. This brings us to minus 1.03. Using this standardization, we can conclude that the probability our player has a score which is less than 3.5 is equal to the probability that a standard normal distribution is less than minus 1.03. We can visualize this as the area under the bell curve to the left of minus 1.03. In an ideal world, we'd be able to open up our formula book, look up this value, minus 1.03, and get our final answer from there. Unfortunately, the formula book only contains data for positive values of z. This means that we'll have to rephrase our problem so we end up with a positive value. Well, by the symmetry of the normal distribution, the probability that you're less than minus 1.03 will be equal to the probability that you're greater than plus 1.03. Since the total probability must add up to 100%, or 1 in decimal form, the probability that you're greater than 1.03 will be equal to 1 minus the probability that you're less than 1.03. Thankfully, we can find this probability by looking up page 36 of our formula book. The first 2 digits, 1.0, tell us which row in our table we should go to. The third digit, 3, tells us the column. When we look at the entry in this row and column, we see that the value is 0.8485. This tells us the area of the red region. But remember, we wanted the purple region, which was 1 minus the red region. So the final answer here will be 1 minus 0.8485, which comes out as 0.1515. In part B, we're told that a random sample of 64 Galway players has a mean score of 3.74. Based on this, a local newspaper claims that Galway players have a different mean score to the players in Ireland. In part I, we must use this information to construct a 95% confidence interval for the mean score of all Galway players. We should use the standard deviation of 0.36 in our calculations. We are working with a normal distribution here, and we're asked to find a 95% confidence interval. Thankfully, there's a direct formula that we can use to find this interval. It's the interval x bar plus or minus 1.96 times sigma over root n. Unfortunately, this result doesn't appear in the formula book, so it's something you'll want to have memorised before your exam. Here, x bar represents the sample mean, and we were told this was 3.74. Sigma is the standard deviation, and we're told to use a standard deviation of 0.36. Finally, n represents the sample size, and we have a sample of 64 players. Let's sub these values in. We can use our calculator to simplify the right-hand portion of this expression. It all comes out to 0.0882. Next, we'll need to deal with this plus-minus sign. This means that we should split into two cases, one with a plus and one with a minus. In the context of confidence intervals, the lower bound is obtained by using the minus, and the upper bound is obtained by using the plus. To finish off, all we have to do is to compute these two quantities. The lower bound comes out as 3.6518, and the upper bound comes out as 3.8282. In part BII, we must carry out a hypothesis test at a 5% level of significance to test the newspaper's claim. There's 4 things that we're prompted to do. State the null hypothesis, the alternative hypothesis, state our conclusion, and also justify the reason for our conclusion. Well, the newspaper's claim is that Galway players have a different mean score to players in Ireland. So we're interested in comparing the score of Galway players versus the overall average of all Irish players. When we do hypothesis testing, the null hypothesis tends to include equality. In other words, it's often in the form something is equal to something else. In this context, our null hypothesis is that the mean score of Galway players is equal to the mean score of Irish players. To find the alternative hypothesis, we need to consider what happens if the null hypothesis is not true. Here, the null is stating that two things are equal, so the alternative will simply be the statement that these two things are not equal. In other words, the alternative hypothesis is that the mean score of Galway players is not equal to the mean score of Irish players. To make our conclusion, we'll need to rely on the relationship between hypothesis testing and confidence intervals. In the previous part of the question, we found a 95% confidence interval for the mean score of Galway players. It was 3.6518 to 3.8282. One way to think of this is that we're assigning 95% confidence that the true mean is within these bounds. Well, if we're assigning 95% confidence to be inside the interval, then the remaining 5% will be for being outside the interval. The null hypothesis states that the mean score of Galway players is equal to the mean score of Irish players. If this were to be true, we would expect, with a 95% confidence, that the mean score for Irish players would be inside this 95% confidence interval. Well, in part A, we were told that the mean score for Irish players is 3.87. This value does not lie inside the confidence interval, and this can be viewed as evidence that the null hypothesis is not true. So the conclusion here is that there is sufficient evidence to reject the null hypothesis and conclude that the mean score of Galway players is not equal to the mean score of Irish players. In part C, we're told that a national newspaper conducts a survey on a random sample of N teenagers in Ireland. 35% of them said they play the online word game every day. Based on this, a 95% confidence interval was created for the percentage P of all teenagers in Ireland who play the game every day. Correct to one decimal place, the interval was from 26.5% to 43.5%. We must use this information to work out the value of N, the number of teenagers surveyed. The key to solving this question is the following result. For a 95% confidence interval, the margin of error for a percentage is given by E is equal to 1.96 times the square root of P hat times 1 minus P hat all over N. Here, E represents the margin of error, P hat represents the sample proportion, and N represents the sample size. If we can figure out what E and P hat are, then we can do some algebra and solve for N. Well, P hat is the sample proportion, and we're told that 35% of the sample play the game every day. So here, P hat is 35%, which as a decimal is 0.35. The margin of error, E, is the distance between an endpoint of the confidence interval to the center point. Whenever we construct a confidence interval, we always do it around the sample proportion or sample mean. So the center point of the interval here will be the 35% we found as P hat. We can compute the margin of error by finding the distance between the upper bound, 43.5%, and the center point, 35%. This gives us 8.5%, which as a decimal is 0.085. Alternatively, we could have found the distance from 26.5% to 35%, and we would have got the same answer. Now that we found the values of P hat and E, let's put them into our formula. We want to solve for N here. In other words, we'll want to isolate the N all by itself on one side of the equation. A good place to start would be to strip away some of the layers of this expression on the right-hand side. The 1.96 represents multiplication, so this can be removed by dividing both sides by 1.96. Next, we can target the square root. The inverse of a square root is a square, so to get rid of this, we can square both sides. Looking at the right-hand side, the n is underneath the line in a fraction. This is a bit awkward. We can get it out of here by multiplying both sides by n. Now, we're pretty close to having n all by itself. The only issue is that it's being multiplied by an expression. To get rid of that, we should divide both sides by that expression. If we do some calculator work to compute the right-hand side, we end up with n is equal to 120.9639. N represents the number of teenagers, and this must be a whole number. So to get our final answer, we round to the nearest whole number. N is equal to 121. Part D says that a player wins the game if they guess the word with 6 guesses or less. The organisers of the game have recorded the following statistics for players in Europe. 80% of players win the game each day. 90% of players who win the game will play it again the following day. And 25% of players who do not win the game will play it again the following day. We must use this information to fill out the provided tree diagram. We're given a written description of the tree diagram, but I'll skip over it here because most of it is visually clear from the diagram itself. In our diagram, we're told that 360,000 people played the game on the 1st of June. Each of these players either won or lost the game, and this is the first split in our diagram. We are told that 80% of players win the game each day, which as a decimal is 0.8. That's why we have a probability of 0.8 leading to the win box. Well, if 80% of the players win, then the remaining 20% of players will lose. As a decimal, that's 0.2. So we can write the probability 0.2 on the branch to the lose box. To find the number of people who won and lost, all we have to do is multiply our total population of 360,000 by these probabilities. So, for the win box, we'll have 360,000 times 0.8. This gives us 288,000. For the lose box, we'll have 360,000 times 0.2. This gives us 72,000. Now we can think about the 2nd of June. We know that 90% of players who win the game will play it again the following day. As a decimal, that's 0.9, and that's why we have a 0.9 coming out from the win box. 25% of players who do not win the game, or lose the game, will play it again the following day. That's why we have this 0.25 coming out from the lose box. To fill in these two play boxes, all we have to do is multiply the previous number by the given probabilities. 288,000 times 0.9 comes out as 259,200. 72,000 times 0.25 comes out as 18,000. From here, we just need to repeat the process we've just done twice more. Once in the upper half of the tree and once in the lower half of the tree. Starting with the upper half, of the 259,200 people who played on the 2nd of June, 80% or 0.8 will win and 20% or 0.2 will lose. We can multiply by these probabilities to get the number of players who win and lose. Remember, 90% of players who win will play again the following day. So if we have a box labelled win, we should multiply by 0.9 to find the number of those players who play the following day. 25% of players who lose the game will play again the next day. So if we have a box labelled lose, we should multiply by 0.25 to find the number of those players who will play again the next day. Filling out the remaining entries in the lower half of the tree works in a very similar way. Of the 18,000 players who play on the 2nd of June, 80% or 0.8 will win. Multiplying these numbers tells us that we have 14,400 winners. 90% of players who win the game will play again the next day, so to find the number of these people who play again on the 3rd of June, all we have to do is multiply by 0.9. This gives us 12,960. Backtracking a second, of the 18,000 players on the 2nd of June, 20% or 0.2 will lose. Multiplying 18,000 by 0.2 gives us 3,600. 25% of players who lose will play again the next day, so to find the number of these people who play again on the 3rd of June, all we have to do is multiply by 0.25. This gives us 900. In the final part of the question, we're told that one person is picked at random from those who played the game on all 3 days. We must find the probability that this person lost on the 1st of June, 2nd of June, or on both. The first step here will be to figure out how many people actually played the game on all 3 days, 1st, 2nd, and 3rd of June. Well, we're in luck here. The way the tree diagram is structured is to track the number of players who make it through all 3 days. So to find the number of people who played on all 3 days, we simply need to see the amount of people who made it to the end. In other words, we should add up the values in each of the final 4 play boxes. When we do this, we end up with 213,444. So, how many of these people lost a game on the 1st of June, 2nd of June, or both? Well, the 186,624 in the top box represents the players who won on the 1st of June and won again on the 2nd of June. So these guys didn't lose on either day. The 12,960 in the second box represent the players who won on the 1st of June, but lost on the 2nd of June. So these guys did lose on one of the days. The 12,960 in the third box is for the people who lost on the 1st of June and won on the 2nd of June. So again, this represents players who did lose on one of the days. Finally, the 900 people in the last box lost on the 1st of June, and lost again on the 2nd of June. So these guys also lost on one of the days. To find the total number of people who lost on the 1st of June, 2nd of June, or both, we must add together the numbers from these three boxes. 12,960 plus 12,960 plus 900. This gives us 26,820. To find the probability of picking such a person, we must divide this number by the total number of people who played on the 3 days. This gives us 26820 divided by 213444. If we simplify this fraction, it comes out as 745 over 5,929. Or as a decimal, we can write it as 0.125654.